Bismillahirrahmanirrahim. Today we will study chapter 4, that is regarding thermochemistry and fuels. In first chapter of our internal combustion engine, we have studied the basic terminologies, components of the engine. In second chapter, we have studied the operating characteristics, different equations and different parameters, how we will find them. And in third chapter, we have studied engine cycles for SI engines and CI engines, 4-stroke and 2-stroke. Now in chapter 4, we will study thermochemistry and fuels. Basically, the thermochemistry, the first, in this chapter 4, there are 2 lectures. In first lecture, we will deal mostly about the chemistry and the organic chemistry regarding the fuels. Now, combustion reactions. Most IC engines obtain their energy from the combustion of hydrocarbon fuel with air. As we already know that combustion of hydrocarbon fuels with air, we get the heat energy, which converts chemical energy of the fuel into internal energy in the gases within the engine. The maximum amount of chemical energy that can be released heat from the fuel is when it reacts combust with the stoichiometric amount of oxygen. So a correct amount of fuel with correct amount of oxygen, then we get the maximum amount of the chemical energy. If there is some variation, we will not get this maximum amount of chemical energy. So the stoichiometric oxygen, sometimes called theoretical oxygen, is just enough to convert all carbon in the fuel to carbon dioxide and all hydrogen to H2O with no oxygen left over. Let's see. The balanced chemical equation of the simplest hydrocarbon fuel, that is methane. Simplest hydrocarbon fuel which we have is methane, that is CH4. Burning with stoichiometric oxygen is CH4 plus 2O2, which will give us carbon dioxide plus 2 mole of water vapors, 2H2O. So it takes 2 moles of oxygen to react with 1 mole of fuel, and this will give 1 mole of carbon dioxide and 2 moles of water vapor. Now, if the isooctane is the fuel component, now instead of methane, we are using isooctane fuel. The balanced stoichiometric combustion with oxygen would be C8H18 is the isooctane fuel plus 12.5 O2, means 12.5 moles of oxygen, and it will give us 8 moles of carbon dioxide and 9 moles of water vapor. So this how your chemical equation will be balanced. Now, the molecules reacts with molecule. So in balancing a chemical equation, molar quantities, fixed number of molecules are used and not mass quantity. Remember this thing. We used fixed number of molecules and not the mass quantities. 1 kilogram mole of a substance has a mass in kilograms equal in number of to the molecular weight, molar mass of that substance. So mass of one is equal to nm, where m is the small m is the mass, capital N is the number of moles, and capital M is the molecular weight. In SI units, 1 kg mole of methane is equal to 16.04 kilograms, and 1 kilogram of oxygen is equal to 32 kilograms, and 1 kilogram is equal to 6.02 multiplied by 10 is to 26 molecules. This for your info. Now, atmospheric air is made up of different elements, in which we have 78% nitrogen by mole, 21% of oxygen, 1% of argon, and few traces of carbon dioxide, neon, methane, helium, and water vapor extra. But nitrogen and argon are essentially chemical neutral and do not react in the combustion process, as we have seen in our previous equations. But their presence, however, does affects the temperature and pressure. But as they are major portion or major contributor of the air, so their presence affects your temperature and pressure in the combustion chamber. To simplify calculations without causing any large error, the neutral argon in the air is assumed to be combined with neutral nitrogen, and atmospheric air then can be modeled as being made up of 21% of oxygen and 79% of nitrogen. So to ease our mathematical calculation and further analysis, we take 21% of oxygen and 79% of nitrogen and is a complete air. Okay. For every 0.21 mole of oxygen, there is also 0.79 moles of nitrogen. Or 1 mole of oxygen, there are 0.79 divided by 0.21 moles of nitrogen. So for every mole of oxygen needed for combustion, 4.76 moles of air must be supplied. That 4.76 contains 1 mole of oxygen plus 3.76 moles of nitrogen. Now, the basic equations which we have read previously, stoichiometric combustion of methane with air is then CH4 plus 2O2. Now, 2 plus into 3.76 of nitrogen. Now, the products will be carbon dioxide, 1 mole of carbon dioxide, plus 2 moles of water vapor, plus the same amount, this 2 into 3.76 of nitrogen. And for isooctane fuel with combustion with the air, we have C8H18 plus 12.5 O2. So we have 12.5 into 3.76 of air nitrogen. The products will be 8 mole of carbon dioxide, 9 mole of water vapor, and 12.5 into 3.76 of nitrogen. The molecular weight of 29 will be used for the air. So we will use 29, the molecular weight of the air in our calculations. Combustion can occur within limits. When more than stoichiometric air is present, the mixture will be lean, or when less than stoichiometric air is present, the mixture will be rich for given amount of a fuel. Now, if methane is burned with 150% stoichiometric air, the excess of oxygen ends up in the products. So instead of 100% stoichiometric air, we are having 150% of stoichiometric air, means 50% more. So now the chemical equation for the simple methane will be CH4 plus 3O2 plus 3.76 into nitrogen, 1 mole of carbon dioxide, 2 moles of water vapor plus 3 moles of nitrogen, 3.76 plus an excess air will be oxygen will be there. Excess oxygen will be there. Okay. If isooctane is burned with 80% stoichiometric air, means deficient of 20%. So the instead of 100%, the ideal amount of the air, we are using 80% of the stoichiometric air, the theoretical air. So it is deficient of 20% air. So there will be not enough oxygen to convert all the carbon to carbon dioxide, and carbon monoxide is formed in the products. Let's see how this forms. So we have isooctane C8H18 plus 10O2 plus 10 into 3.76 and 2 will give us 3 moles of carbon dioxide, 9 moles of water vapor, plus 5 moles of carbon monoxide, plus 10 into 3.76 of nitrogen. So due to shortage of 20% of oxygen. The end product we will receive 5 moles of carbon monoxide, which is not desirable. Carbon monoxide is a colorless, odorless, poisonous gas which can be further burned to form carbon dioxide. It is formed in any combustion process when there is a deficient of oxygen. When we have a deficiency of oxygen, the product will also be carbon monoxide beside the carbon dioxide. It is also very likely that some of the fuel will not get burned when there is a deficiency of the oxygen. So this unburned fuel ends up pollution in the exhaust of the engine. So with carbon monoxide, we will have some unburned fuel also. Now, various technologies is used for the amount of air or oxygen used in combustion. 80% of stoichiometric air is equal to 80% theoretical air is equal to 80% air means 20% deficiency of air. Now, 133% of stoichiometric oxygen means 133% theoretical oxygen. 133% oxygen means 33% excess of oxygen is available. Now, for actual combustion in an engine, we know the equivalence ratio is a measure of the fuel-air mixture relative to the stoichiometric conditions. So it is defined as phi, the equivalence ratio, phi fuel-air ratio actual divided by fuel-air ratio stoichiometric, or air-fuel stoichiometric divided by air-fuel actual, where Fa is mass of fuel divided by mass of air, fuel-air ratio, AF is equal to mass of air divided by mass of fuel, air-fuel ratio. Ma is mass of air, Mf is your mass of fuel. When your phi, the equivalence ratio is less than 1, it means your mixture is lean, oxygen in the exhaust. We have excess of oxygen, and in the end product, we will have a oxygen as a excess amount. When phi, your equivalence ratio is greater than 1, means rich mixture, we have less of oxygen. So when we have less of oxygen, one of the end product is carbon monoxide and fuel in the exhaust. When phi is equal to 1 means we have ideal condition. We require the same amount of fuel, we require the same amount of oxygen. In ideal condition, the stoichiometric theoretically, maximum energy released from the fuel. SI engines normally operates with an equivalence ratio in the range of 0.9 to 1.2 depending on the type of operation. So the range for an SI engine, the equivalence ratio range is 0.9 to 1.2 depending upon the types of operation. Now in this figure, let's see the combustion efficiency as a function of a fuel equivalence ratio. Efficiency for engine operating lean is generally on the order of 98%. When an engine operates fuel rich, there is not enough oxygen to react with all the fuel and combustion efficiency decreases. CI engine operates lean and typically have higher combustion efficiency. Now on x-axis, we have fuel equivalence ratio from 0 to 1.6. And on y-axis, we have combustion efficiency in percentage. Now, when phi equivalence, fuel equivalence ratio is 1, we have this line, and portion on this left side is a lean mixture. We have an excess amount of air, so the combustion efficiency is 98% here in this lean region. When we have a rich mixture, means less of oxygen, the combustion efficiency will drop with the increase in the fuel equivalence ratio. Okay, at 1, we have in lean region up till 1, we have 98% of combustion efficiency, means 98% of the fuel is combustible, having a combustion with the oxygen. But in the rich region, We have less oxygen, so the end product will be carbon dioxide plus water vapor plus carbon monoxide and some fuel particles in the exhaust. And CI engines operates normally in lean region, whereas SI engines operate from zero point 0.9 to 1.2 region. So in this region, your SI engine operates and CI engine usually operates in this lean region, less than 1. Okay. Now we have example. Fuel is isooctane is burned with 120% theoretical air in a small 3-cylinder turbocharged automobile engine. We have to calculate air-fuel ratio, fuel-air ratio, equivalence ratio. So we have isooctane fuel and 20% excess of oxygen. So let's see. Stoichiometric reaction is C8 H18 plus 12.5 O2 plus 12.5 into 3.76 and 2, we get 8 moles of carbon dioxide plus 9 moles of water vapor plus 12.5 into 3.76 of nitrogen. So this is the stoichiometric reaction or the balanced chemical equation. Now we are having 20% excess of air. So 20% more oxygen. So the equation will be C8H18 plus 15O2. So instead of 12.5, now we have 20% more. So it's 15 moles of oxygen plus 15 moles of nitrogen, 3.15 into 3.76 nitrogen. The end products are 8 moles of carbon dioxide plus 9 moles of water vapor plus 15 into 3.76 of nitrogen plus 2.5 moles of oxygen. That is the excess oxygen which we will receive in the products. Okay. Now, with 20% excess air, all the fuel get burns and the same amount of carbon dioxide and water vapor is formed in the products. In addition, there is some oxygen and additional nitrogen in the products, the excess air. So we know these equations 2-55 and 4-1 are used to find the air-fuel ratio. So air-fuel ratio, we know that mass of air divided by mass of fuel. So converting into molar factor, and we know the Na multiplied by Ma divided by Nf, Mf. So 15 is the ratio, 4.76 is the air, and 29 is the molecular weight divided by 1 into 114 molecular weight of the isooctane. So the air-fuel ratio comes out to be 18.6. Now the fuel-air ratio, this was air-fuel ratio. Now the fuel-air ratio, mass of fuel, mass of air, or we can simply say 1 over AF. So it comes out to be 0.055. The fuel-air ratio of stoichiometric combustion, fuel-air ratio of stoichiometric combustion, putting the value in the equation, we get 0.066. Now, equivalence ratio, fuel equivalence ratio, phi is equal to fuel ratio, fuel air actual divided by fuel air stoichiometric. So we get 0.833. So it comes in a lean region. Okay. Now, chemical equilibrium. General chemical equation, we have specific VA into A, VB, B. These are the reactants and the products are VCC plus VDV, where A, B represents all the reactant species, whether 1 or 2 or more, and C and D represents all products regardless of the number, then VA, VB, VC, VD represent the stoichiometric coefficient of A, B, C, D. Equilibrium composition for this reaction can be found if one knows the chemical equilibrium constant, Ke. So Ke is found from this equation where this is the description. Now, Ke is very dependent on temperature. What is Ke? K is your chemical equilibrium constant. That chemical equilibrium constant is very dependent on temperature, changing many orders of the magnitude over the temperature range experienced in an IC engine. As we know, when we have a intake stroke, the temperature varies from TDC to BDC. When we have a compression stroke, the temperature varies from BDC to TDC. When we have a combustion, temperature varies. Now, from when we have a power stroke, from temperature varies from TDC to VDC. Then we have exhaust stroke. Then there is a temperature variation. So there is a wide range of temperature variation in this IC engine. So as the chemical equilibrium Ke gets larger, equilibrium is more towards the right, the product side. This is the maximizing of the entropy. For hydrocarbon fuels reacting with oxygen air at high engine temperatures, the equilibrium constant is very large, meaning that there are very few reactants, fuel and air left at final equilibrium. However, at these high temperature and other chemical phenomena take place that affects the overall combustion process in the engine and what ends up in the engine exhaust. And that chemical phenomena is known as dissociation of normally stable components, which will occur at these higher engine temperature. How this dissociation take place? It is at high temperatures. Your carbon dioxide dissociate to carbon monoxide and oxygen dissociate to monoatomic oxygen, and nitrogen dissociate to monatomic nitrogen. At high temperature, we get this phenomenon. This not only affects the chemical combustion, but is a cause of one of the major emission problem of IC engine. Nitrogen as diatomic N2 does not react with other substances, but when it dissociates to monatomic nitrogen at high temperature, it readily reacts with oxygen to form nitrogen oxides, NOx, basically known as NOx. Nitrogen monoxide and nitrogen dioxide, a major pollutant from automobiles. So this association converting of stable components into highly reactive components. So this is the result. To avoid generating large amount of nitrogen oxide, combustion temperature in the automobile engines are lowered, which reduces the dissociation of nitrogen. So to avoid getting NOx in the combustion chamber and in the exhaust, we have to lower the temperatures of the engine so that there is less of a dissociation of these nitrogen, oxygen, and carbon dioxide. Unfortunately, when we lower the temperature, this also lowers the thermal efficiency of the engine. When exhaust gases of an IC engines are cooled below their dew point temperature, water vapor in the exhaust starts to condense to liquid. It is common to see water droplets comes out of an automobile exhaust pipe when the engine is first started and the pipe is cold. So in the morning or in winter, we see normally this phenomenon. Very quickly, the pipe is heated above the dew point temperature and the condensing water is then seen only as vapor when the hot exhaust is cooled by the surrounding air, much more noticeable in cold winter time. Now, combustion temperature. Previously, it was combustion equilibrium, now combustion temperature. Heat liberated by combustion reaction of an hydrocarbon fuel with air is difference between the total enthalpy of the product and total enthalpy of the reactant. So the heat liberated by the combustion reaction of hydrocarbon fuel with air is difference between the total enthalpy of the products and the total enthalpy of the reactants. This is called heat of reaction, heat of combustion, or enthalpy of reaction, and is given by the equation Q is equal to summation of products NiHi minus summation of reactants NiHi, where Ni is the number of moles of component I, HI is HFI plus delta HI. HF is the enthalpy of the formation. The enthalpy needed to form 1 mole of that component at standard condition of 25 degrees Celsius and 1 atmospheric pressure. Delta HI is the change of enthalpy from standard temperature of our component I. Now combustion temperature Q will be negative, meaning that the heat is given up by the reacting gases. Value of HF and delta HI are molar specific quantities. Now, heating value QHV is the negative of the heat of reaction for 1 unit of fuel and thus is a positive number. It is calculated assuming both the reactant and the products are at 25-degree atmospheric condition. Here must be used when using heating values, which almost always are given in mass units, kilojoules per kilogram, whereas heat of reaction are obtained using molar quantities as in equation 4-5. Two values of heating values are given in the table. Higher heating value is used when the water in the exhaust product is in liquid state, and lower heating value is used when water in the product is in vapor. Remember this thing. Every fuel have two heating values. One is higher heating value, one is lower heating value. When you are having a high heating value, it means water in the exhaust product is in liquid state. When we have a lower heating value of that fuel, it means that water in the product is in vapor form. Q higher heating value is equal to Q lower heating value plus delta H vapors, enthalpy of vapors. Okay. Higher heating value is usually listed on the fuel containers. Generally, we find that higher heating value is listed on the fuel container, the higher number making that fuel seems more attractive. For engine analysis, lower heating value is logical values to use. On container, we will having a higher heating value that seems more attractive. But for analysis of an engine, we must take the lower heating value. That is a logical way to use that. All energy exchange in the combustion chamber occurs at high temperature and only somewhere down the exhaust process where can no longer affect the engine operation does the product gas gets cooled to the dew point temperature. Heat into the engine and that gets converted to output work can be given as Q in is equal to combustion efficiency, mass of fuel, Q, heating value. Now here we have L. So L is your lower heating value. An estimation of the maximum temperature reached in an IC engine can be obtained by calculating the adiabatic flame temperature of the input air-fuel mixture. This is done by using the equation based on Q is equal to 0. So summation of product NiHi is equal to summation of reactants NiHi. Now let's see what is the adiabatic flame temperature is. Now adiabatic flame temperature, assuming that inlet condition of the reactants are known, assuming that the inlet conditions of the reactants are known, it is necessary to find the temperature of the product such that this equation will be satisfied. This is the adiabatic flame temperature. Now, adiabatic flame temperature is the ideal theoretical maximum temperature. Adiabatic flame temperature is the ideal theoretical maximum temperature that can be obtained for a given fuel and air mixture. The actual peak temperature in an engine cycle will be several hundred degrees less than this. Why? Answer to why is there is some heat losses even in the very short time of one cycle. Combustion efficiency is less than 100%. So a small amount of fuel does not get burned and some component dissociate at high engine temperature. All these factors contributes to making the actual peak engine temperature somewhat less than the adiabatic flame temperature. So adiabatic flame temperature, the ideal theoretical maximum temperature will be always greater than your actual adiabatic flame temperature. Now, talking about the hydrocarbon fuels, and that too, the first one is the gasoline. Gasoline, the crude oil, is made up of almost entirely of carbon and hydrogen with some traces of other species. It varies from 83% to 87% carbon and 11 to 14% of hydrogen by weight. Crude oil is a combination of your carbon and hydrogen, and carbon in a range of 83 to 87%, and hydrogen in a range of 11 to 14% by weight. The carbon and hydrogen can combine in many ways and form many different molecular components. There are a number of ways in which hydrogen and carbon combines together and form different molecular compounds. The crude oil mixture, which is taken from the ground, is separated into components products by cracking and or distillation using thermal or catalytic method at an oil refinery. So crude oil, which is the basic oil which we extract from the ground, is then undergone these two chemical processes. One is cracking and other is distillation using the thermal or catalytic method at an oil refinery. Cracking is the process of breaking large molecular components into a more useful component of smaller molecular weight. So we crack the larger molecules to smaller molecule by weight. Preferential distillation is used to separate the mixture into single components or small range of components. So these two are the method which are used for the crude oil to generally, the larger the molecular weight of the component, the higher is its boiling temperature. A oil which is having a large molecular weight of a component, the boiling temperature will be higher. Low boiling temperature components, smaller molecular weights, are used for solvent and fuel gasoline, while higher boiling temperature components with large molecular weights are used for tars and asphalts or returned to the refining process for further cracking. So smaller ones are used as fuel and solvents in gasoline, while the larger molecular weights are used for tar and asphalts or returned to the refinery for further cracking. The various components of different molecular weights will vaporize at different temperature. So in an oil, various components of different molecular weights will vaporize at different temperature. Smaller molecular weights boiling at lower temperature and larger molecular weights at higher temperature. A small percentage of components that vaporize boil at low temperature is needed to assure the starting of a cold engine. So in an oil, we must have the combination of different molecular weights. Okay. Why? A smaller percentage of components that vaporize boil at low temperature is needed to assure the starting of a cold engine. Fuel must vaporize before it can burn. However, too much of this front end volatility can cause problem when the fuel vaporizes too quickly. But remember, your fuel should not be of so much of that smaller component by weight that it should vaporize too easily. And if it vaporizes too easily and too oftenly, then we will have a problem. The volumetric efficiency of the engine will reduce if we have this too much of this front end volatility. If the fuel vapor replaces air too early in the intake system. Another serious problem this can cause is a vapor loss. First, it will if we have a more front end volatility. First, the volumetric efficiency will be less. Second problem is the vapor lock, which occurs when fuel vaporizes in the fuel supply lines or in the carburetor in the hot engine compartment. When this happens, the supply of fuel is cut off and the engine is stopped. So we will have a vapor lock in this condition. Now, a large percent of fuel should be vaporized at the normal intake system temperature during the short time of the intake process, that is the front end volatility. To maximize volumetric efficiency, some of the fuel should not vaporize until late into the compression stroke and even into the start of the combustion. So, in order to maximize the volumetric efficiency, some of the fuel should not vaporize until late into the compression stroke and even into the start of the combustion. This is why some high molecular weight components are included in the gasoline mixture. So gasoline mixture is a combination of small molecular weight and high molecular weight. Okay. If too much of this high end volatility is included in the gasoline, however, some of the fuel will never get vaporized and ends up as exhaust pollution or condense on the cylinder wall and dilutes the lubricating oil. Now, problem is this: if we have too much of this high end volatility, means the fuel did not burn late in the combustion. So what will happen? The sum of the fuel never get vaporized and ends up as the exhaust pollution. So some that unburned fuel will be in your exhaust emission or condense on the cylinder wall and dilutes the lubricating oil. So thermal properties of the lubricating oil will be disturbed. Now, hydrocarbon fuel gasoline. One way that is sometimes used to describe a gasoline is to use three temperature. The temperature at which 10% is vaporized, at which 50% is vaporized, and at which 90% is vaporized. Let's read this statement. Temperature vaporization curve for a typical gasoline mixture. The component which vaporize at low temperature are called front-end volatility components and are useful for starting coal engine. Those components which vaporize at the highest temperature are called high-end volatility components and increase engine volumetric efficiency. This gasoline could be classified as 57, 81, 103 degrees Celsius. 50% of the gasoline would be vaporized at 81 degrees C. Let's see the graph. On x-axis, we have percentage evaporation from 0 to 100. On y-axis, we have temperature from 0 to 110 above. Now, at 10% here, 50%, at 57 degree, 10% evaporation at 57 degree. Okay. 50% evaporation at 81 degrees Celsius and 90% evaporation at 103 degrees Celsius. Now, whenever you go to a market and you buy a gasoline fuel in barrels, on your barrels, there's gasoline classification with respect to temperature must be written. Remember this thing. If you buy large amount of fuel for your company or your for an organization, on the fuel barrels, this temperature classification should be there. It will tell you that at this temperature, the 10% vaporization is there. At this temperature, 50% vaporization will be there. And at this temperature, 90% vaporization will be there. So this temperature ranges should be mentioned on your fuel barrel. Remember this thing. If it is not mentioned, then there is something wrong with the fuel barrels. Okay. Now, some common hydrocarbons which we are used in practice. Carbon atoms form four bonds in a molecular structure, while hydrogen has one bonds. A saturated hydrocarbon molecule will have no double or triple carbon to carbon bonds and will have a maximum number of hydrogen atoms. Saturated hydrocarbon molecule will have no double or triple carbon to carbon bond and will have maximum number of hydrogen atoms. An unsaturated molecule will have double or triple carbon to carbon bonds. Let's see. Family of hydrocarbons, we have paraffins, we have olefins, we have naphthalene, Aromatics, general formulas are here. Molecular structure is chain, chain, ring, ring. Saturated, unsaturated. So they are saturated means the no double and triple bond. Here we have double and triple bond, no double and highly unsaturated. So these are the stability. Let's see. Mixture of hydrocarbons with different molecular structure with some amount of sulfur, oxygen, nitrogen impurities. Mixture of hydrocarbons with differing molecular structures with some amount of sulfur, oxygen, nitrogen, and impurities. Hydrogen and carbon atoms linked in different ways, giving it different chemical and physical properties. If we change the structure or the combination of hydrocarbons, hydrogen and carbon, the chemical and physical properties will change. We will see the difference in physical and chemical properties between different types of hydrocarbon depend upon their chemical composition and affect mainly the combustion process. Now, first the common hydrocarbon component, that is paraffin. The paraffin family, sometimes called alkanes, are chain molecules with the carbon hydrogen combination of CnH2n plus 2 being any number, n being any number. The simplest member of this family and the simplest of all stable hydrocarbon molecule is methane, CH4, which is the main component of the natural gas. So methane, CH4, here we see CH4 molecules of hydrogen. Other species of this family include propane, C3H8, butane. We have a 4 carbon and 10 hydrogen. Now, prefix for hydrocarbon fuels, if we have number of carbon atom in main or chain or rings, 1 to 12, so we prefix are methane, meth, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane, undecane, dodecane. Now, paraffins, sometimes the chain in the molecules are branched and other molecules structure are obtained with same number of carbon and hydrogen atoms. One of such isomers is isobutane, which has the same chemical formula as butane C4H10, but has different structure. Now, let's see isobutane C4H10. So this is the chemical structure. Isooctane, so we have this. It can also be called as 2,2,4 trimethylpentane. Now, a few other paraffins. 2-ethylpentane, we have C7H16. So this will be the chemical structure. 2-methyl, 3-ethyl, C9H20. So this will be the chemical structure. Now, paraffin series. Straight chain molecular structure, general formula is CN2H2n plus N. Isobutane is the isomer of butane, so methane, ethane, propane. We have butane and isobutane. Now the second common used hydrocarbon component is olefin. The olefin family consists of chain molecules that contains one double carbon to carbon bond and therefore called unsaturated. So the olefin family consists of chain molecules that contains one double carbon to carbon bond and are therefore unsaturated. The prefixes from table 4.2 are used with suffix "ene", ethene, butene, butene, isobutene. So ethene is C2H4, in which we have carbon to carbon double bond, and then we have two hydrogen bonds with each carbon. So butane is this, and butane 2 is like this. Now, straight chain molecular structure like paraffin, but contains one or more double carbon bond, that is like this. General formula is CnH2n. Monoolefin has one double bond, whereas diolefin has two double bonds. This is diolefin, okay? Now, diolefins are chain molecules similar to olefins except that they have two double carbon to carbon bonds. These unsaturated compounds have the chemical formula CnH2n-2 and use suffix diene, 2,5-heptadiene. So this is the chemical structure. Now, another common hydrocarbon is acetylene. The acetylene family has unsaturated chain molecules with triple carbon to carbon bond. In diolefin, we have double carbon bond. In acetylene, we have triple carbon to carbon bond. And the chemical formula is CnH2n-2. The best known member of this family is acetylene, C2H2. So chemical composition is like this. Another common hydrocarbon is cycloparaffin or naphthenes. Same chemical formula like olefin, but with ring structure. Now we have this ring structure. General formula is CnH2n. So cyclopentane is the common cycloparaffin. And lastly, the aromatic series. Ring structure compounds having benzene as central structure. So general chemical formula is CnH2n-6, in which a carbon has a single to single bond and double bond. So this is the benzene and this is toluene. Another common hydrocarbon is alcohol. Alcohol similar to paraffins with one of the hydrogen atom replaced with the hydroxyl radical OH. The most common alcohols are ethyl alcohol or methanol, CH3OH, in which a carbon having a 3 hydrogen, then oxygen and OH radical. Then ethyl alcohol or ethanol or propyl alcohol or propanol. So with this come to ends, please refresh your second year organic chemistry. So thank you very much for this lecture. Rest we will cover